This conference will now be recorded.
Hello, everybody. Jordan Girth here with the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 88. Today's presentation, Elevated Mix Layers and the new CIMSS Weighting Function webpage. Our presenters are Chris Gitro, meteorologist in charge from the Weather Service Forecast Office in Duluth, Minnesota, and Scott Lindstrom, a scientist and trainer at the Cooperative Institute for Meteorological Satellite Studies, CIMSS, in Madison, Wisconsin. Our facilitator for today is Carl Jones, the meteorologist and satellite focal point at the Weather Service Office in Grand Forks, North Dakota. Just a few reminders before we get started that this session is being recorded, so you'll have an opportunity to share it with your colleagues that can't join us today. There will also be an opportunity for Q&A after the presentation. We encourage participation, particularly from field office and regional headquarter participants. Please post your question in the chat and we will field them as they are asked. Encourage you to sign in with your full name or note your name when asking a question if you are using an office or general account, so we can always follow up if we need to. We are looking for future presenters for the Satellite Book Club. We're headed toward 100 Satellite Book Clubs in June, so please help us out, reach our goal. If you have an application you'd like to share with the field, get in touch with us. And if you're looking for training materials, Office of the Chief Learning Officer and Brian Mata can help with that. I'd like to thank our TowerS team, particularly Kushad Bowman, the Office of the Chief Learning Officer, the GOZAR, and the JPSS programs for their help. And of course, thanks to all of you for being with us and our presenter and facilitator. Without further ado, I'd like to introduce both Scott and Chris, starting with Chris first. Chris spent 20 years in the Air National Guard as a weather officer while simultaneously pursuing a career at the Weather Service. He is currently at his 5th weather office since joining the Weather Service 16 years ago. So glad to have Chris. And Scott Lindstrom grew up a mile from the Penn State meteorology building. He received 2 bachelor's degrees at Penn State and went on to graduate school at the University of Wisconsin-Madison, where both his parents and 4 grandparents graduated as well. Scott creates training documents, quick guides, and blog posts in collaboration with the Forecast Training Division and Weather Service. He also enjoys looking at beautiful satellite imagery and explaining the benefits of using it. So Scott and Chris, welcome to the Satellite Book Club.
All right, thank you everybody. Can everybody hear me okay?
Hear you great.
All right, fantastic. All right, well, let's go ahead and talk a little bit about some elevated mix layers and the new CIMSS weighting function. Kushad, if we can go to the next slide, please. All right, so just a brief overview of what we're going to talk about. The first part is going to be my part. I'm going to talk about elevated mix layers, why they're important and where they come from. We're going to talk also a little bit how we got here from some of the early research on elevated mix layers to present day, where we're able to use satellite imagery to talk and track elevated mix layers with time. And then we're going to do a very brief case study, just looking back at this past weekend severe weather event across the Central Plains and also down across the Deep South, multiple tornadoes, and unfortunately we had fatalities on the south side of Des Moines as well. And then I'm going to turn it over to Scott, and he's going to talk about the new weighting functions webpage and some of the applications for using that for tracking and sampling elevated mix layers. So Kushad, go ahead to the next slide, please. So what is the elevated mix layer? Well, basically it's a warm air advection process, dry air or over the higher terrain, Mexican Plateau, the Rockies, etc. Boundary layer heating occurs over those areas, and that warm layer actually gets advected eastward or northeastward with time, and that actually eventually overrides moist boundary layer air, typically from the Gulf of Mexico, and that separation between the dry air aloft and the warm or the boundary layer moist air, typically from the Gulf or another moisture source, that's what we call the cap or the lid. And that really helps prevent the vertical mixing and suppresses convection to just some isolated storms here and there. And that also allows for the poleward low-level moisture advection via a process called underrunning as well. So moisture is actually able to lift north or work its way northward with time. But really it's that lid that really suppress this thunderstorm development because of the atmosphere being stable, and that helps increase convective available potential energy or CAPE. And then eventually the cap breaks down and we get to severe thunderstorm development. It's a very significant severe weather maker or process that occurs. And they're very common in the spring across the central and southern plains, but as we'll see throughout the course of this presentation, they do move geographically based on the season. So that's something that we're starting to get a little bit better picture of now that we have satellite technology and we're able to track these features in real time. Kashad, if you can go to the next slide, please. So kind of understanding the cap and the processes and how it's created. This is a graphic from my former weather office. I used to be a lead forecaster at the Kansas City office, and one of my fellow forecasters, Dan Halblitzel, created this graphic back in 2016, and we posted this on social media. And I couldn't think of a better image to throw in here just to kind of highlight how the elevated mixed layer develops. Dan's my counterpart down at the Twin Cities office now, just down to myself, and this I think is probably one of the better graphics to kind of just show how an elevated mixed layer develops. So you get the warm heating over the higher terrain surfaces, and that cap, that warm air, it vects eastward over the warm, the moist air that comes north from the Gulf of Mexico, and that's how you get the cap. Next slide, please. So talking about some of the seasonal variability, typically this time of year, as we start to get close to the April, May, June timeframe, our main source regions for the elevated mixed layers are going to be the higher terrain surfaces across the desert Southwest, the Mexican Plateau, etc. However, that gradually starts to shift northward with time, and we're starting to see and recognize that a little bit more. So it's not uncommon towards the middle to the latter half of the summer months to see the elevated mixed layer source regions originate from the Central Rockies, Northern Rockies, and at times even the Canadian Rockies. These lead to some pretty significant severe weather situations further on downstream as that elevated mixed layer it vects eastward with time. Next slide, please. So how we got here, this is, I think, looking back at the 60s or 50s and even in the 60s, Toby Carlson really helped pave the way for understanding what the elevated mixed layer is. He was a meteorologist instructor at professor at Penn State University. And for years and years and years, we tracked these using soundings from balloon launches that are done twice a year. And we've done that for many, many years. But once we got into the 2000s, we started to leverage some of the satellite technology that's available to us. So I remember probably in the late 2000s, early aughts, watching a Visit Go Sounder training session by Scott Beckmeyer. He kind of really introduced the concept of being able to track elevated mixed layers with satellite imagery using the Go Sounder with time, and I was kind of really interested in that. And then back in 2010, Pete Banakis and Mike Exter from Burlington and Taunton office released a Northeastern U.S. severe weather paper, and that was pretty much, I was hooked from that point forward and looking at elevated mixed layers and tracking these, and we just continued to start to gain a little bit more and more understanding of it. And so in 2014, I presented a poster on using the Go Sounder to track elevated mixed layers at NWA. And then from that point forward, topic gained a little bit more traction at the GOZAR Users Conference in Kansas City, and then finally later on in 2015, Dan Bickus released probably one of the first segments of training highlighting the future capabilities of the GOZAR satellite for tracking elevated mixed layers in time. So we really started to put the puzzle pieces together during the 2010s, and really it's research to operations. And over on the right, that's an animation from, I was a forecaster at the Binghamton, New York office back in 2012, and we had a pretty good severe weather event, EF1 tornado in Elmira. And I remember working this day thinking that we were going to have convection further on south across central Pennsylvania. Well, it turned out we had convection right along the state border between New York and Pennsylvania. And if I would have looked at this in real time, I would have seen that from the Go Sounder imagery, we were pretty much capped across central Pennsylvania. And I started to really understand and look for those interfaces between the warm brightness temperatures of where an elevated mixed layer is, the gradient areas, and looking for the convective development as a result of that. So if we can go to the next slide, Kashad. But it turns out we could have done this sooner, but we didn't know. So one of the perennial severe weather events I remember growing up, I was a kid in Buffalo, New York, watching. We had the Canadian channels, and I was a big hockey fan back in the day, and still am, and a big Wayne Gretzky fan. And I remember the summer of 1987 just being glued to the TV because there was this F4 tornado in Edmonton, Alberta. Well, it turns out that this was the second deadliest tornado in Canadian history, and this is a classic example of seeing an elevated mixed layer come off a higher terrain surface from somewhere else aside from the Mexican Plateau, Southern Rockies, etc. So you can see this. I think this is GO7 sounder imagery, and Dan Bicus from Colorado Sierra was able to get this, and we could see it, the actual warm layer, the warm brightness temperatures advecting northeast with time into southern Alberta. So thought that was kind of neat to show, but we didn't know that at the time, but we're starting to understand this now a little bit better. So Kashad, you can go to the next slide. Here's another example. This is from May 2000. Talking with Dan Bicus quite a bit. This is one of the events that he recalls and being just a classic example of being able to track that elevated mixed layer eastward with time. Great sounding from Jonathan Finch at Dodge City. You could see well-pronounced elevated mixed layer steep mid-level lapse rates through the middle portions of the sounding. And if you go to the next slide, Kashad, you can see, fairly significant severe weather event over a 2-day period across the plains, into the upper Mississippi Valley, and eventually all the way over into the northeastern U.S. So just threw this in there to kind of highlight the fact that these are pretty significant severe weather producers, and it's very important for us to track these with time. So if we go to the next slide. So fast forward to present day. I'm not going to spend a lot of time on this slide. We all know we got the GOES-R series satellites. Dan talked a lot about it last week at the Satellite Book Club. We know they're a lot better. So having 5-minute imagery available to us that's got roughly about a minute latency in AWIPS, our ability to track these today is much greater than it has ever been before. Whereas the GO sounder imagery, we got one image per hour if we were lucky. So if we go to the next slide. So let's talk a little bit about this past weekend, and this was kind of a marathon Scott and I did try to get this presentation together. So this event happened 4 or 5 days ago now, and just to give you a little bit of an idea of what the synoptic setting was, I won't spend a lot of time on this, but we had a trough across the Central Rockies that was going to kick out east across the Central Plains, take on a negative tilt throughout the day. Along the surface, we had a cold front with a dry line that was extending eastward through the Central Plains as well. And we had a lot of convection that developed across northeastern Kansas, southwestern Iowa, southeastern Nebraska as a result, as that dry line surged eastward with time. Next slide. So looking at this past weekend a little bit in more detail. So over on the right, we have the 0Z sounding from Topeka, Kansas. We do have some steep mid-level lapse rates, but if you look at the animation on the left-hand side, you can see that the really steep mid-level lapse rates appear to really work in to the Central Plains and during the overnight hours. And that's right from the SBC meso-analysis graphics. You can see that, we got dry mid-level lapse rates within that 700 to 500 millibar layer. And it really appears that that really worked in during the overnight hours. Go to the next slide. You can see that by 12Z, you got those really steep mid-level lapse rates there in the middle portions of the atmosphere. In fact, you got your steepest mid-level lapse rate there is about 9.1 degrees Celsius per kilometer, and that definitely appeared to really take hold during the overnight hours as that elevated mixed layer worked into the area. Go to the next slide. So looking at a weighting function, and Scott will talk a little bit more about this later on here in the presentation. This is the band 10 weighting function, and you can see that it's really peaking out in the lower levels there at 12Z at about 753 millibars, and I just approximated the best I could and drew a black horizontal bar there on the sounding from Topeka to kind of give an idea. This shows that the sounders actually, the ABI imagers actually with band 10 is actually sampling further down into the atmosphere and capturing that elevated mixed layer quite well. Go to the next slide. So here's an animation from this past weekend. You can see the warm brightness temperatures in the band 10 imagery really starting to advance northeastward into the area during the overnight hours. It looks like we have some convection that develops over on north central and northeastern Kansas during the early morning hours. And this animation goes from about 21Z on Friday afternoon through 0Z on Sunday. So it's a roughly about 18 hours or so, or 15 hours or so. But you could see that the convection across northeastern Kansas during the early morning hours around 12Z lifts northeastward with time. And then as that occurs, that trough is coming in, taking on a negative tilt. And you can see the warm brightness temperatures from on the band 10 imagery really start to surge back up into north central Kansas and eventually northeastern Kansas out ahead of that trough that was approaching and taking more and more of a negative tilt with time. So secondary reinforcement of the EML throughout the day potentially. I think with the convection that occurred during the morning hours, we probably had a little bit of diabatic heating. There was probably some alteration of the lapse rates as a result of that. And then you could see in the band 10 imagery how that just resurged northward with time, with the convection eventually developing during the mid to late afternoon hours along that dry line cold front as it started to move into southwestern Iowa and northeastern Kansas. I can go to the next slide. So here's the 12Z sound, or sorry, the 0Z sounding from Topeka. You can see that, we got really steep mid-level lapse rates extending all the way down past almost to the 850 millibar layer. And you can see on the left-hand side at 0Z from the SBC mesoanalysis page there that we got that finger of steep mid-level lapse rates extending north up the Missouri River Valley there towards the Omaha area, Council Bluffs area. And, sure enough, that's where we had a lot of significant convection develop during the afternoon hours on that day. Go to the next slide. Oh, actually, Kishad, if you go back one thing I also want to point a picture of is if you look at Colorado extending east, Dodge City, northeast up into the Omaha area, that seems to be a source region there. But if you look further south as well, over the Mexican Plateau, southeastern Texas, extending northeast into the deep south, that seems to be another source region for an elevated mixed layer. And we're going to talk a little bit about that as we go forward here in the next couple of slides. Kishad, go ahead with the next slide, please. So this is the new capsule lapse rates animation from 4 to 6 March, and you can actually see the red temperatures there across the Central Rockies, advecting northeastward with time, and then further to the south across the Mexican Plateau, Southwest Texas, Deep South Texas, etc. You can actually see those warm temperatures start to advect northeast across the Deep South with time. So I think we talked a lot about this past event, and we had 2 good days for severe weather, and it really looked like the portions of the lower 48 were being impacted by EMLs with 2 different source regions on this day. So, the Central Rockies served as a source region, Great Basin, Four Corners region for the convection that developed over the Central Plains and mid-Mississippi Valley, whereas further south across the Mexican Plateau, Deep South Texas, that served as a source region for elevated mixed layer air that worked into Louisiana, Arkansas, etc., that led to severe weather development on Sunday in tornado activity down across Arkansas, and I believe even in the western Tennessee, if I'm not mistaken. But just got through the circles on there, and you can actually track that with time. So I thought that was a pretty neat thing, and kind of really highlighted the fact that we had EML source regions potentially, it looks like, from 2 different source regions this past weekend. You can go to the next slide. All right, so this is just a quick summary, like a 48-hour graphic of the band 10 imagery, as well as a 48-hour loop of the mid-level lapse rates on this day. So, you can see across the Central Plains, it seems like at least to us anyways, that the source region is from the Central Rockies, advecting northeastward with time ahead of that mid-level trough, and then further south, it looks like to us there's another source region there across the Mexican Plateau, advecting northeast into eastern Texas, etc., into the deep south. So it looks to us as though we had 2 different source regions for elevated mixed layer air for this past weekend severe weather activity. And I believe that concludes my portion. Oh, actually, I think I got one more slide. Kashad, if you want to go ahead and, yep. So some EML tracking tips. I remembered I threw this in here at the very last minute. So talking with Dan Bicus, we've talked a lot about this over the past couple of years. So if you really want to, track elevated mixed layers, and, we feel that, it's absolutely essential to do so, because, the further they get away from their source regions, it could have some big implications on severe weather development over your particular area. So the first thing you really want to do is you want to confirm on soundings that it is that it is in fact an elevated mixed layer, and there's probably no better way to do that than looking at soundings. Remember, they're characterized by mid-level warm advection from a source region, so it's actually a warm advection process as they advect east and northeast away from their source regions. And after confirming, you could track the EML with time on satellite imagery via the band 10 low-level water vapor imagery, or the advected layered precipitable water imagery. And just out of time, we didn't have an opportunity to really show that. But Sheldon Cusselson did a nice little case study on this past weekend as well. And then just beware of downstream convection. I think we may have had that as an example here, because the diabatic heating from convection can modify the elevated mixed layer environment, actually increase the lapse rates a little bit. So kind of like makes the lapse rates a little bit less steep. So that's probably one of the main reasons why it's rare to see elevated mixed layers work all the way into the northeastern US, because there's convection upstream across the Ohio Valley, central Great Lakes, etc. But when it does happen, it's a pretty big event, and some of the more significant severe weather events in the Northeast from Pete Benakis's and Mike Dexter's work are associated with elevated mixed layers that actually survive all the way to the Northeast. So pretty neat thing, in my opinion. I've been fascinated by these for many years, and I just look forward to continue to be able to look at these in real time. So I think that's probably it for my area, and then I'll go ahead and now turn it over to Scott.
Thanks. Next slide, Kashad. So there, as advertised, maybe you're familiar with the old CIMSS waiting function site. There is a new CIMSS waiting function site. The URL is shown there. I'm just going to step through here a little quickly to show you some features of it. And of course, waiting functions are a way to quantify what's going on with the enhanced mix layer. So next slide, please. So if you click on Plot Viewer, there are lots of other things to click on as well, but click on Plot Viewer and that takes you to the main page. Go to the next slide, please. That has 3 different drop-down menus that are circled in yellow. The default, for some reason, is to be GOES 17, and that's a band 13 image. And you see all those points there that are data from the GFS on a 5-degree lat-long grid, and you can look at stuff from 0Z and 12Z. Go to the next slot, please. Next slide, please. So across the top there, you have different things in these pull-down menus. You can look at the GFS model, which has those 5x5 points, or you can look at RAOBs. Next slide, please. You can look at GOES 16, 17, or Himawari data. So you can look at much of the globe, from the Indian Ocean all the way over to Africa. And on the next slide, please, you can see when I put this together back on February 14th, and you have about a week's worth of data that's available there. By special request, you can have the data, old data, be inserted into that. So if you're working on a case study and you want to look at weighting functions for example, from the Iowa derecho in 2020, we can put that information into this website and it'll show up for a while. Next slide, please. So here's just an example. I've chosen Little Rock, and we have a weighting function. By default, it just shows the water vapor weighting functions. It's not showing the weighting function for the window channels or for band 15, which has a peak slightly above the surface. And you also see on the right-hand side there the temperature and dew point profiles, but it's giving you the kind of information that you would expect. Band 8 has a peak that's fairly high in the atmosphere. Band 10 has the lowest peak, and band 9 is intermediate between those. If you blow up those values, next slide, please. If you blow up the values along the bottom, you see exactly where the peak is. So band 8 is peaking at 407 millibars and has a brightness temperature, a computed brightness temperature from the radiative transfer model that's being used to create these of -33, and there's also information there for band 8 and band 10. Go to the next slide, please. So I thought, well, I'd look at the image in Little Rock. So this is the band 8 image, and I've sampled it there. So you see the actual brightness temperatures along with the computed brightness temperature from the radiative transfer model that's being used to compute the weighting function. I saw them and I thought, well, they don't really match very well, but I was assured that that was a pretty good match, and I'm being too particular. And when you look at these weighting functions over the course of time, you'll notice that different pressures show up a lot. So you'll see 555.17 millibars a lot, and that's because that's one of the levels in the radiative transfer model. So the radiative transfer model has a finite number of vertical levels, so you don't have an infinite number of peaks. You get something that's within 5 millibars or something like that. So next slide, please. So then I thought, well, let's look at the actual Little Rock sounding on this particular day and see where those values fall. So we have the 400 millibar, 400, whereas 407 millibars, well, that's on the sounding, it's -27.3. And if we look at where is -33 degrees, we notice it's at 360 millibars. So it's just a way of looking at the information from the weighting function and then relating it to back to the reality of the sounding or of the water vapor channel. So next slide, please. And then here I'm showing you, if there was one thing I would change on this, it's the sounding. So those are the same soundings. The Little Rock one on the left in the weighting function, and also the Little Rock one from AWIPS in N#. They look a lot different to me, but so always have different ways of looking at the thermodynamic data when you're trying to evaluate exactly what's going on. But you see the information there. That I think that's the important information, that it's telling you where's the information that the water vapor channel is sensing, where's that mostly coming from in the atmosphere. Next slide, please. So here's the example from last weekend. This is from Dodge City, showing a very nice peak in the lowest part of the atmosphere. So next slide. So here's what the actual sounding looked like. And if I were to show that to you and ask you if there was an elevated mix layer in that, and I hope you would say yes, you can see that very steep lapse rates from 850 all the way up to 600 millibars or even higher. And it's saying that the peak level for both band 8 and band 10 here around 515 millibars. Band 8 is up around 496 millibars. So there's very little water vapor above those layers that's going to be intercepting any of the upwelling radiation at those wavelengths. Next slide, please. Here's just an example. I was looking at turbulence probability fields, which is a product that tells you what's the likelihood of moderate or greater turbulence. And I also have the water vapor channel on the top, and on the bottom I have the GFS lapse rates. And you might ask yourself, why would I choose 400, 300 millibars for the lapse rate to compare it to the turbulence probability field? Because the turbulence probability does use the 6.19 micrometer as part of its input, and I use the weighting function. So if you go to the next slide, you see the weighting function for Minneapolis on that date had a peak in band 8 around 400 millibars. So that's why I'm using the 400 to 300 millibar lapse rate versus any other lapse rate that I could have gotten from the GFS. Next slide, please. This is there. I mean, there was an old site, and maybe when you do a web search for CIMSS weighting function, you'll still go to the old site, but you'll notice at the very top of that in blue, there's a link to the new site. So it's pretty easy to find the new site if you accidentally end up at the old site. And the old site still works. It just doesn't have all the capabilities. It doesn't have the GFS data. So you're limited to just RAOBs. Next slide, please. I think I'm almost done here. Yep, summary. So the important information you get from the weighting function is, where is the satellite sensing the data? information is coming up from the atmosphere. What level is it coming from? If it's cloudy, of course, it's coming from the top of the cloud. So these are all clear sky computations. So it takes the temperature and the moisture information, puts it in a radiative transfer model, and does some clear sky information. And so it's all going to be a clear sky. And if you have clouds there, the information is just coming from the cloud top. I guess that's all. I see we're at the bottom of the hour, so we should stop for questions because there's lots to ask about maybe. Take it away, Carl.
All right. Thank you, Chris and Scott. That was a pretty good sell, I would say, in using this new weighting function capability. And just seeing some of the comments, it seems like it stirred up a lot of excitement, and hopefully we get to see some use within some future use. But before we start getting into a discussion, I'd like to encourage the field offices and regional headquarters to stay on and participate in discussion, and as well as for attendees to specify their full names in chat when asking a question. Also, if you have any feedback for the Satellite Book Club, please complete the survey that will be posted in the chat room. And it looks like Lee just posted that in there. And before we get into discussion again, here's a preview of next week's Satellite Book Club. And a week from today, on Thursday, March 17th at noon Eastern, Tim Garner, the meteorologist in charge from the National Weather Service Spaceflight Meteorology Group, will discuss satellite usage in support of crewed spaceflight. And if you have any questions for the Satellite Book Club or for configuration of satellite products, please contact the Towers S team. That'll be Lee Byerly and Kashad Bowman. And again, please submit any questions within the chat or indicate if you'd like to ask a question verbally within the chat. And so it looks like we have maybe a couple of questions and comments within the chat. I'll go ahead and kind of read off what has been said so far within the chat. Bill Schoberg said, great. He thought some great use of the gridded new caps, and Ken Pryor also echoes that, mentioning the lapse rate calculation is a great application of new caps. Looks like Tim Schmidt dropped in a link to the new weighting function webpage. So if you haven't seen that yet, you can look within the chat and get the webpage. Daniel also mentions that this is a great resource, and thanks for the new page and interface. We actually have a question from Bill Line. He's actually asking, would operational folks be interested in a pop-up weighting function feature in AWIPS similar to the pop-ups QT for analyzing infrared and water vapor imagery? I think that's a great question. And that actually, I'm not sure, maybe Chris, since you're tied in with operations, what would you think of that potential use?
Yeah, I've been asking for weighting functions in AWIPS for years, so absolutely.
All right. Short and sweet, Chris is on board. I actually will echo that sentiment. I think that would be really helpful. Yeah, so also some an additional question that I guess was actually, might have already been answered, but I'll go ahead and bring it up again. But you mentioned that these are clear sky calculations, and if you mentioned that if the skies are cloudy, that you're starting to get information from the top of the cloud. Does that mean like the weighting function calculation might not be as trustworthy, or how would we be able to interpret when we're actually analyzing imagery where clouds are present?
Yeah, you wouldn't want to be using the information from the weighting function there, because it's saying it's clear skies and you know that it's cloudy. I'm kind of curious about the weighting function in AWIPS though. I'm not certain how math intensive the retrieval calculations are. So I don't know if you would have to send like a gridded field, or if you could do this hourly. I mean, it's an interesting question. I haven't really thought about it. I think it'd be great. So I look forward to that in in an AWIPS build in maybe 2020, late 2022. We'll see how fast they can get that in.
Yeah, and it would be interesting since this new website is already pushing out, you know, the peak where it's sensing the peak of the weighting function. If even just that information would, you know, suffice when trying to determine.
Right.
It could be as simple as that. Well, simple in a loose term, I suppose, right?
It's a simple matter of programming, as they say.
Right. Yeah, so thank you for that. And looks like we have another comment from Nick. Says NewCaps has something called the averaging kernels, which are similar in concept, but instead shows sensitivity of the retrieval to perturbations in the true profile. We are introducing these into operational net CDF output files. Thanks for that comment, Nick. And looks like we have another comment, or actually question, maybe directed at Chris from Michael. Has your capability to sense, track, and use EMLs been diminished at all going from employing the GOES 8 sounder to using the GOES R series API derived data?
Wow, GOES 8 sounder. I think it's been greatly improved just based on the temporal and the spatial resolution improvements with the new ABI imager. So, and, you know, based on that, I would say that it's just been greatly improved since going all the way back to like the mid 80s in that one case that we showed.
All right, thank you, Chris.
Yeah, there was a 7.3 on the GOES 8 on the GOES sounder. I think it was, and this is a trivia question for Tim Schmidt, maybe. What channel number was that? I think it was 16 out of the 22. But yeah, it's so much better now.
I agree.
And would it be, I guess, kind of looking even further on for the next series of geostationary satellites, the GeoXO program, with talk of adding or reintroducing rather the sounder and even maybe even hyperspectral sounder type capability, would that give a little more trustworthiness, I guess, in getting these weighting functions? Would that be something that would be yeah?
Well, GeoXO has, I think it's a 5.1 micrometer, which is even another water vapor channel that's even lower in the atmosphere. Even lower in the atmosphere, I think.
That's correct. We're planning on a 5.15 micron band for the GeoXO imager. That's in addition to whatever additional capabilities are on the hyperspectral infrared sounder.
All right. It's interesting. Looks like we have a comment from Mike Stavish talking about the EML in the West. We may not be normally find ourselves focusing so much on source regions or even labeling air mass regions as EMLs per se. Another warm season application here may be monitoring subsidence inversions and their impact on fire weather. The lowering of subsidence inversions on the terrain often leads to potential significant increase in fire behavior with warming, drying. So this is a good application for the West. Thank you for sharing that, Mike. That's good to hear that there's additional application outside of severe weather analysis. And we've got some more comments coming in. They're starting to flow in pretty nicely. Tim Schmidt says the GeoXO sounder, the GXS, will allow for more vertical temperature and moisture information and some wind information as well. Thank you, Tim. And then Steve Miller also commented, the EML is a very important topic. When looking at the recent example, there is obvious frontal features or frontal structures. How does one disentangle the effects of the EML from frontal dynamics, which produce those warming features in the subsidence zone unrelated to the elevated terrain and vertical motion related to the potential vorticity advection and mechanical lift that is not so dependent on the surface heating. In breaking an EML cap, no, I'm sorry, my apologies. I read that as a comment and not a question. So Steve, actually, if you're capable of unmuting yourself, maybe you can kind of ask it in how you were meaning to ask instead of my translation.
Oh, sorry for such a convoluted question, but yeah, I'm not an expert in the elevated mix layers, so it's really a naive question probably. But when I looked at the example, the recent example from March, what I was seeing first and foremost was what I typically would expect to see from a frontal situation, and maybe I wasn't looking at the right things, but I saw the dry air and the cold sector, which often shows up as a warming in the water vapor imagery. And then, of course, the strong convection along the front from the dynamics of the front itself. So with that in mind, I was wondering, how does the forecaster, maybe it's easy to do, disentangle just the effects of this kind of mixed layer effect, where you could maybe not even have frontal dynamics around, and just this case here where we had an obvious storm system. I guess I was just trying to understand how to disentangle those two signals.
I guess I could take a stab at that. This is Chris. I think one of the main things we want to do is kind of watch the evolution of the mid-level worm brightness temperatures and where they're coming from, a potential source region, etc. And we want to kind of confirm with soundings whether or not there's a true elevated mix layer being sampled by soundings as they're launched twice per day or more, if we're lucky during a severe weather situation and stuff like that. But I think your comment's pretty spot on in the sense that it's not uncommon looking at low-level water vapor imagery to see frontal features by any stretch of the imagination. I've looked at many cases where the frontal features are readily apparent. However, having a pretty good idea of the overall synoptic situation and being able to retrace the elevated mix layer from its actual source region with time is pretty paramount, I think, in order to be able to separate frontal features down near the surface versus the elevated mix layer that's going to be sampled not at the surface by any stretch of the imagination, but definitely in the mid levels of the atmosphere. Hopefully that helps answer some of your questions.
Yeah, thanks, Chris.
Absolutely.
All right, thank you for bringing up that question and answering that, Chris. We are starting to run 45 after the hour, so it should be time to wrap it up. Really love the discussion and the questions that were coming in. We have a couple of additional comments in the chat I'll bring attention to just quickly. Matt Gunsher mentioned that there is a contact on the weighting function webpage, and if you have any bugs or if you want to share how you're using it, feel free to find that contact on the webpage function. Then Ken Pryor also shared a link to near real-time UCAP sounding profiles. Thank you for both of that. I'll pass it to you, Jordan.
All right, thank you, Carl, and thank you so much to our presenters today. Chris Gitro coming back to join us again this week, and Scott Lindstrom, long-term colleague of mine at the University of Wisconsin-Madison. I hope Field takes advantage of this new weighting function webpage and applies it to some of the forecast challenges that come along with the EML this coming spring and summer. As always, the Satellite Book Club will continue next week, Thursday, March 17th. Tim Gardner from the Spaceflight Meteorology Group is going to be talking about satellite data usage in support of crewed spaceflight. So hopefully you find that interesting. In addition, feel free to get in touch with our TowerS team, Lee Byerly, Kashad Bowman. If you have any questions about the Satellite Book Club or the configuration of satellite products, you can see their email addresses there or find them in the TowerS chat room on NWS chat. I'll just wrap up today by noting that all things are good so far with GOES-T. Be another 2 weeks or so before all of the launch and orbit settling is complete, but we'll try to give you intermittent updates on GOES-T for those of you particularly in the West that are interested about that. Very busy schedule to calibrate it and get it ready for operational use by August 1st. So really excited about that. Okay, we're 1 minute over. Thanks so much for joining us today. Thanks again to our presenters, our moderator, and all of you for being with us. Take care. Stay well.